Technology has really come a long way when it comes to location finding. From the seafarers using the stars to find their way back home to right now, we use Google Maps or other similar navigation apps on our smartphones to do the same thing. And these devices, they are darn good at it too. But the question still remains, what is really happening? How does it work? Is it magic or is it mathematics? So let's find out what is really happening. What is the mathematics under the hood that makes this whole concept work, that we can use our phone to actually find out where we are at a particular point in time. GPS stands for Global Positioning System, and it uses satellites orbiting Earth to determine our location. There are two imaginary lines all over our Earth's surface that are used to figure out where anything is on the face of the Earth, and they are the longitude and the latitude. Lines of longitude are vertical and run from north to south, while lines of latitude are horizontal and run from east to west. The early seafarers used the stars to find out the longitude and latitude of their location, but in modern times we use our smartphones to do the same thing. It's way easier, and our satellites do the whole lifting when it comes to finding out the longitude and latitude of our location. So here's how it works. The whole idea is as follows. The US Global Navigation Satellite System has over 30 satellites. GPS uses the constellation of satellites orbiting Earth twice a day to determine longitude and latitude. These satellites in orbit communicate with receivers down here on Earth. These receivers could be anything from radios, computers, and yes, you guessed it, smartphones. Receivers get signals from these satellites at about 300 million meters per second. This is the speed of light, and the receivers use this formula to determine how far they are from the satellites sending the signal. The signal speed is the speed of light, while the signal time is the time taken for the signal to reach the receiver from the satellite. So let's say a satellite sends a signal to a smartphone, and the time it took the signal to reach, according to the calculation from the smartphone's quartz clock, is 0.07 seconds. This means that the smartphone is about 21 million meters away from the satellite. But this only tells us about the distance from the satellite and not the location. This is where the math gets cooler. So for the location of the phone to be able to be determined, we need a process that is called trilateration. Did I hear you ask what is trilateration? Well, have no fear. Trilateration is a way of locating something by knowing the distance of three other objects from that thing. Because we are using three objects to do this, thus the tri in trilateration. In our case, the objects we are considering are 3 out of over 30 location satellites in orbit. But before we go into orbit, let's make things a little bit easier, shall we? Assuming we have a rat located somewhere on a 2D plane or the Cartesian plane, but we don't know where the rat really is. We don't have the information. However, news got to us that a cup of known location is 2 meters away from the rat. This is valuable information, but not good enough to give us the exact location of the rat. The best we can deduce is that the rat can be anywhere in a 2-meter radius from the cup. But if we know of another object, say a sock, that is 4 meters away from the rat, this narrows down our search to just 2 points. But which of the 2 points is the rat located at? This is where the third object, say a screwdriver, comes to the rescue. Now the screwdriver is 3 meters away from the rat. Now this third metric has exposed the exact location of the rat. Awesome. The example we just gave right now all happened in a 2D plane. But when we deal with the satellite and the phone, we're talking about 3D space here. But don't worry, the same concept is applicable too. So, say a satellite is 21 million meters away from a smartphone. It is 21 million meters away from every direction, thereby creating a sphere of distance instead of a circle, like the case of the rat. So when we have 2 more satellites with their respective distances from the smartphone, we succeed in getting an accurate position of the phone. But this is not where it all ends. I wish it were that simple, but unfortunately, it's not. So here's the thing. The clocks on those satellites don't tick at the same rate as clocks here on Earth. And it's not one effect, it's 2, and they fight each other. First, these satellites are moving very fast, about 14,000 kilometers per hour. Wow! And Einstein's special relativity tells us that moving clocks tick slower, so the satellite clocks falls behind ours. But at the same time, The satellites are about 20,000 kilometers above us, where Earth's gravity is weaker. And Einstein's general relativity tells us that clocks in weaker gravity tick faster. So the satellite's clocks races ahead of ours. So which effect wins? Gravity does, and the satellite clocks end up ticking faster than ours by about 38 microseconds every day. 38 microseconds is like nothing. But remember our formula. Distance equals speed times time. And the speed we're multiplying by is the speed of light. Tiny errors in time become massive errors in distance. Without correcting for this, your GPS will drift off by about 10 kilometers every single day. Your phone will think you're in a different city by the weekend. How do engineers fix this? That is what we'll unpack in the next video. So make sure you subscribe so you don't miss it. Hello there, I am Chukwudi, and I just don't teach mathematics, but I try to explain and to show you why it works so that you will understand it better. And that will be all for today's video. I'll be seeing you in the next one. Have a lovely day and goodbye.